And we are going to start this subject of fluid mechanics, and first of all we will discussing the properties of the fluid. The first topic is the properties of the fluid. So you all know what is a fluid. The layman definition of a fluid is something which can flow. The fluid includes liquid and gas which can flow. That is the layman's definition. The first question which is asked from this subject of fluid mechanics is, what is a fluid? How do you define a fluid? In an interview, and if you say like this as an engineer or a scientist, that or a subject the student of science, not scientist, that something which can flow, that is good, but it is not recommended to define fluids like this. So we will define what is fluid based upon the rate of deformation, the shear strain rate. And we will be discussing the properties of fluids, various properties of fluids, how the fluids behave, why do they behave like this, what is surface tension, and what is capillarity, what are the cohesive adhesive forces, and what are their roles in these properties, and how do we represent the density of the fluid, what is specific gravity. And apart from that, we will discuss some phenomena, like we have the Archimedes principle, that is the principle of buoyancy, or when the fluid is submerged in a body, it displaces submerged in some, when a solid body is submerged in a fluid, the fluid is displaced, so the buoyancy force is acting. So this we will be discussing along with the Bernoulli's equation, modification of Bernoulli equation, because you know that these equations are applicable for ideal fluids only. So fluid mechanics has got two parts, statics and dynamics. One is fluid statics and other is dynamics. It has further two parts, kinetics and kinematics. So here we will be discussing all these. Statics means the fluid is at rest, like water in a pond or in a container, anywhere, but it is not moving, it is at rest. In a dam, so it is applying the force on the surface. So we have to find the pressure applied on a surface, the force applied on that surface because of that. So when the water is not moving, or any other fluid, that is discussed under statics. The pressure measurement also by using different types of manometers discussed under this subject of statics. Then we have dynamics. So we have to consider the inertia forces of the fluid or acting on the fluid when it is moving, and we have to consider, or we have to study the velocity and its other parameters like acceleration, displacement, etc. of a fluid. So these are studied under kinetics and kinematics. So we are starting with the introduction part, that is the fluid and its properties. First of all, let us discuss what is a fluid. We come across a definition generally for the fluid, a definition of a property of the fluid, that is called viscosity. So you all know what is viscosity. Viscosity means stickiness. Oils, if you touch the oil with your hand, you will find that it is sticking with the hand, the fingers. It is sticky, quite sticky. Whereas on the other hand, if you have mineral oils, not the fatty oils, or you have water and you touch it with your hand, you will find that it is not sticking to your hand. It is not that sticky as the fatty oils or other oil. So the first one, which is having stickiness, is called a viscous fluid. The second one is non-viscous, like water is non-viscous as compared to oil. Now what is this viscosity? For this, let us discuss this phenomena. Suppose this is a surface, stationary surface, and over this surface the fluid is moving, and when the fluid is moving at a very slow speed, then the fluid is having regular layers which are called lamina. Laminae, plural of lamina. And if I take a cross section here at any time, then these laminas are moving in a regular manner over each other, such that the surface or the lowest lamina which is in contact with this surface is having zero velocity. Here the velocity is 0, and velocity goes on increasing as we move in this direction. Suppose this is our y direction, so the surface above this is having a velocity, say u, and the surface above this is having another velocity. Suppose the velocity increases by du, so this velocity is du, and distance from this surface where velocity is 0 is measured. So this layer is at a distance y from this surface, and the upper layer is at a distance of y plus dy. This distance is y, this is dy. Let me show this with a separate diagram. Now this layer is having a velocity u, and this is having u plus du. Means up to this, this is also u, this is du. So this additional velocity is du. Now I am taking the distances from here. So this distance is, say, this distance is y, and this is dy. So distance measured from here is y plus dy. So at a distance y from the surface, the velocity is u. At y plus dy, the velocity becomes u plus du. So there is a velocity gradient. Rate of change of velocity with distance, that is du by dy. Now this type of flow is called laminar flow, because flow is regular with no intermixing across the layers. This we will be discussing also again in this chapter. This is just the introduction, and you all know that this is defined by the type of fluid, or the type of flow is defined by the Reynolds number. So we will be discussing this. What is Reynolds number? This is the ratio of inertia force to viscous force. Reynolds number is a dimensionless number, that is inertia force divided by viscous force. So when viscous forces are dominant, viscosity is high and inertia forces are low, Reynolds number will be having a lower value. So the flow will be laminar. And when inertia forces are dominant, that is when the viscosity of the fluid is low, so the layers disappear and there is intermixing of the fluid particles among these or across these layers. In that case we say that this force is high, this force is low, so the Reynolds number increases, and that flow is called turbulent flow. Now come back to this. So what happens here, when a layer is moving in this direction, the upper layer, which is at a higher velocity like this, try to move at a higher velocity, the lower one is having a lower velocity, so the lower one tries to stop the upper one from moving at a higher speed, whereas the upper one tries to drag it in this direction. As a result, both are, because offering friction to each other, so as a result a stress is developed. And what stress is that? That is a shear stress. What is shear? We know that shear is something like slipping of one surface with respect to each other. Like you cut a paper with scissors or hands, the surfaces are slipping like this. Or of a beam, if you apply the force here, if it shears along this plane, so this part moves with respect to this shearing. We have discussed this in detail in the subject of strength of materials in the videos given in the beginning. So a shear stress is developed among the layers. Suppose this is one layer. This is moving in this direction, this is also moving in this direction, but the speed is different. So as a result, a shear stress is acting on the surfaces. Suppose this area over which the shear stress is acting is A. So the shear stress is directly proportional to the velocity gradient. So I can write that tau is equal to eta du by dy, where eta is called viscosity, coefficient of viscosity. Dynamic viscosity. This is called coefficient of dynamic viscosity. And you know that stress is force per unit of area. So I can write that the force acting, or which offers the resistance which causes the shear stress between these two layers, that is equal to A eta du divided by dy. The unit of this you can find later on, we can discuss this also. Unit is tau is having Newton per meter square, and du by dy is having per second. So it is Newton second per meter square, sometimes also referred to as Pascal second. This is called dynamic viscosity. So now come back to our discussion. So when a force is, a shear stress is present in a fluid which is moving, like in this case, suppose when the fluid is stationary. So will it behave in the same manner as the moving fluid? Now before this, let me define the ideal fluid. What is an ideal fluid? The ideal fluid is which is having zero viscosity and which is incompressible, which cannot be compressed. That means the density remains constant. Zero viscosity means eta is 0. The coefficient of viscosity is 0. So you can see that when eta is 0, coefficient of viscosity is 0. So du by dy, that is equal to the strain rate. This is strain rate, which is nothing but the shear strain. So shear strain is equal to tau divided by eta. So when eta is tending towards 0, it is very small. In that case, du by dy is tending towards infinity, even when tau is very small. So even in the absence of any disturbance or any shear stress present, the velocity gradient or shear strain rate or shear deformation, this is very large. So this is how we define a fluid. So we can say that the fluids, even when they are at rest, they deform at their own, or they deform themselves. If you take a small element of fluid, suppose the fluid is contained inside a container. We take a small element of this. So this small element will be deformed at a continuous rate, or continuously it will be getting deformed because of the surrounding fluid, even when there is no stress acting on it. So this is how we define the fluid. Two things I told you. One is ideal fluid, which is having zero viscosity, which is incompressible. So when no shear stress is applied, even then there is significant shear strain which is present in case of a fluid. So this is how we define the fluid. This is the first step, the definition of a fluid. Now let us discuss the properties of the fluid. So now let us discuss the other properties of a fluid after defining a fluid. The fluids have some properties, like we have density, specific gravity, then viscosity of the fluid, capillarity, surface tension, and fluids exert pressure. Now pressure can be exerted by a fluid or a solid when kept on a surface, but we study the pressure and its measurement under the properties of the fluid. It is not necessary that pressure is only the property of the fluid. Pressure is defined as force acting on a unit area normal to this direction of force. So fluids exert pressure when contained in a container, and we measure that pressure because that is a very important phenomena, because we have to measure the pressure. So that's why we are studying it under the properties of the fluids. So these are some of the properties of the fluids which we are going to discuss. So first is density. Density of a fluid, density of any substance is defined as mass per unit volume. The unit of this is kilogram per meter cube, or kilogram per liter, or gram per centimeter cube, gram per ml, etc. In case of a fluid, the density is almost constant, okay, and constant because we consider the ideal fluid to be incompressible. So what is meant by that? When a fluid is flowing, like inside the ocean, when the fluid is at the bottom of the fluid, that part of the fluid which is at the bottom, so this upper part of the fluid, because of its weight, is compressing the fluid below this. So as a result, the density here is higher as compared to the density of the fluid which is near the surface. So this is having lower density. So the density increases because the pressure is increasing with the depth. So as we move down, the pressure increases with the depth, which causes the density to increase. Then we have a term which is called relative density. What is relative density? Relative density is a term which is used to compare the density of a fluid, which may be a liquid or a gas, with respect to another fluid, which is a standard fluid, like water in case of bodies, solids and liquids, and in case of the gases we take air. So relative density, also written as RD or specific gravity, this is defined as density of a substance, means solid or liquid, divided by density of water at 4 degrees Celsius, because water is having maximum density at 4 degrees Celsius. Water density is maximum at 4 degrees Celsius, and this is for solids and liquids. Density of pure water is approximately 1000 kilogram per meter cube. So if you have specific gravity or relative density equal to 0.8 for a substance, it means that density of that substance, suppose it is a solid, equal to 0.8 into density of water, 800 kilogram per meter cube, which is less than the density of water. So if specific gravity or relative density is less than 1, it means that the substance, liquid or that solid, is lighter than water. If it is greater than 1, then heavier than water. Now, relative density or specific gravity for a gas is defined as the density of the gas divided by density of air at normal temperature and pressure conditions. So air is a standard fluid, density of air is very low, around 1.23 or 1.22 kilogram per meter cube, very low as compared to water. So this is how we define the specific gravity, and it is of very this term is quite important when we study the phenomena of buoyancy, when we see that there is a change in the apparent weight of a substance, of a solid, when it is submerged in a fluid. So we will be discussing this property again when we study the phenomena of buoyancy. We will also be discussing the equilibrium of the fluids and equilibrium of a body which is submerged fully or partially in a liquid. Now I am saying here liquid because the gases have very low density. As a result, they do not exert much buoyancy force on the body which is submerged in the gas. Like if you talk about ourselves, so while we are moving in the air, so we are displacing the volume of air which is equal to the volume of our body or the space occupied by the body, and as a result the mass of the air which is displaced, or the weight of the air which has been displaced by our body, that is trying to regain its place. So it is trying to move our body from the place which has been occupied by the body, so applying a force in the upward direction. That is the buoyancy force. But the weight of that air or that quantity of air is negligible because its density is small. Volume may be large, but density is very small. So we do not experience the buoyancy force when we are moving in a gas like air. So this is the property, specific gravity or relative density. Then viscosity we have discussed. Then capillarity. What is capillarity? I am going to give only a brief introduction of capillarity and surface tension, because these will be discussed at length later on. So when we have a very small tube, of very thin tube of small diameter, and it is submerged like this, put into this fluid, so as a result the liquid in the tube may rise up like this. If it is fluid like water, it will rise, and generally the fluids rise. But it is dipped, if it is dipped in a fluid like mercury, it will fall down. There is a depression. So this is, you can see the shape. I will be discussing later on how this shape is affecting the capillarity. Rise, this is rise, capillarity rise. This is a capillary tube, and here this is fall or depression, capillarity fall or depression. So this is fluid like water which rises in glass, and fluid like mercury which falls in glass. The reason we will be discussing later on, and the reason behind this is the forces present here, which are cohesive and adhesive. If cohesive forces, they are dominant, then in that case it is going to fall. If adhesive forces are dominant, it is going to rise. So in brief, this is called capillarity or capillary rise. The one example of this you must have experienced when you put water in an earthen container, earthen pot, generally called matka. So in summer it remains cool. The reason behind this, the earthen pot or the matka is having very small or minute holes in its surface that have very small diameter. Here the ratio of radius or diameter to length for the capillary is a deciding factor whether there is the fluid is going to come out or not. So this also will be discussed later on. So in that case, the fluid is, because of the capillary action, it is coming out at the surface, getting vaporized. As a result, it is taking heat from the surroundings and the water itself, which is the latent heat of vaporization, and the temperature decreases. So water inside that is maintained at a lower temperature. So this is called the capillary action. Now next we have surface tension. So surface tension is the property of a fluid by virtue of which it tries to stretch itself in the form of a film having minimum area of cross section. Now for this I will give you an example that will be sufficient at this level. Suppose I have this bangle made of metal and a thread is put here. This is a loop of the thread. This is wire or bangle, etc. This is also a circular loop, and now you put a soap film here. You put some soap water inside this, so it will make a film like this, soap film. Now the film is formed everywhere. Now what will happen if I puncture the film between this? So can you answer what will happen? If you puncture it, what will be the shape? The shape will be like this. The film is here. We do not do anything to this film, and here we have no film. What is this? The thread. It becomes circular. What is the reason? Because the film tries to maintain the minimum area of cross section. How it is possible? Circle is formed because this thread is pulled by the soap in every direction. As a result, it forms in the form of a circle. So this is called surface tension. We will be discussing the the excess pressure because of the surface tension property inside a soap bubble, inside an air bubble, or so on. That we'll be discussing later on in this. So these are the properties, some of the properties of the fluid which we have discussed. Only the brief introduction of this we have discussed here. So later on we will be discussing them at length. Now I told you about viscosity in the beginning. So let me add something to that. Viscosity is defined in two ways. This, as I told you, is called dynamic viscosity. Means if you measure the viscosity when the forces acting on the fluid are considered, it is called dynamic viscosity. Then there is another viscosity this is called kinematic viscosity. So this new is called kinematic viscosity, and its unit is the viscosity. Eta is having a unit of Newton second per meter square, and this is kilogram per meter cube, and Newton is kilogram meter per second square into second per meter square kilogram per meter cube. So this is kilogram, second cancels out, and meter square per second. Meter square per second. So this unit and Newton second per meter square these are the SI units of the viscosity. So these are the two methods to measure the viscosity, and these values will be given to you while solving the problems. You can also find the Cgs units of viscosity. The SI unit of eta is poise, and that of nu kinematic viscosity is Stokes. Sorry, these are not SI units, these are the Cgs units, because sometimes you will also find the value given in this form. We can convert this dynamic viscosity, the unit is Newton second per meter square. So I can write this as kilogram meter per second square into second upon meter square, which further becomes kilogram per meter per second, which can be written in Cgs equal to 1000 gram by 100 centimeter per second. So this is equal to 10 poise. This is the Cgs unit. Now as far as this second kinematic viscosity is concerned, its unit is meter square per second. This is SI unit. So in Cgs can be written as 100 square centimeter square per second, and this is equal to 10 to the power 4 Stokes. So I can write that 1 poise is 0.1 Newton second per meter square, and 1 Stokes is 10 to the power minus 4 meter square per second. These are the Cgs units. So these are the properties of the fluids, and this is about the first topic. Then next we will be discussing the first of all the pressure. What is fluid pressure and how do we measure the pressure? We will begin with that.